Today it's all about kinetics and the speed of a reaction. That's what we're going to be talking about today. And we're also going to talk about gases. So I find that these two topics really go hand in hand. Now, today's lecture is going to be quite mathematical, involving a lot of calculus. So, you know, if you haven't done calculus, this might be quite difficult. Now, what we're concerned with in kinetics is basically how fast does a reaction take place. In chemistry, there's two main questions. The one is how fast is something taking place, that falls under the realm of kinetics. And the second is, does it take place, or will it spontaneously take place? And that falls in the realm of thermodynamics. So there's always kinetics and thermodynamics. And in chemistry, one generally has sort of the interplay between these two things. Now, what chemical kinetics is really concerned with is measuring the rate of a chemical reaction. And, well, what you see here is actually the rate of the reaction expressed in terms of the change in the concentration of X over the change in time. Now, this is assuming that the concentration of X is the starting material. That's why there's a minus sign in front there. Because of course, if you imagine a transformation X to Y, for example, or a chemical reaction when X just sort of decomposes to Y, the product, then of course, as time proceeds, X is going to go down in concentration, isn't it? Well, let's say X to Y, and Y will go up in concentration. So that's why there's a minus sign. In words, how fast does compound X disappear or is compound Y fall? Okay. So we measure, so this is what the rate is. The rate is essentially the change in the concentration of starting material product with respect to time. Now let's just pin this down. So we have this sort of arbitrary reaction, and we have the change in X over the change in time, and we have a minus sign there because remember it's going to go down in concentration as time proceeds. And for the rates of Y, we're going to have a change in Y over change in T. Now all I've basically done is I've replaced the delta signs with a D, right? This should be square brackets with the concentration. And we do that because that enables us to employ differential calculus, which enables us to explore instantaneous changes as opposed to average changes. So we could get something that looks like this. This is time. Of course, you're going to start with X having a certain concentration, so the y-axis is concentration. This is going to go down, and the concentration, so this is X, the concentration of X. And this will be, for example, the concentration of Y. Notice at T0, the start of the reaction, the concentration of Y is 0, because that the reaction is the start. And basically, the rate of the reaction is the change in the concentration over the change in time. Now, do you notice that these two curves are curved, right? In other words, if you want to measure, let's say the rate of the reaction at this point here for the formation of Y, what would you do? At that one point, you need to do what? You need to measure the gradient of the tangent, right? If you want to measure the average rate between, let's say, this point here, let's call this T1, and this point here, let's call it T2, there you have to, of course, measure the gradients of the line that passes through those 2 points. The gradients of that line would be the rate of the formation of Y in this case. And you can do the same thing for X. And you'll see if you do that for X, the gradient is negative, and that's where the minus sign comes from. So that's basically what we're studying in kinetics, or rates, speeds of reactions. And here we have another example. So this is if we look at the decomposition of hydrogen peroxide to water and oxygen. You can follow this reaction in a sort of a setup like this, basically. The hydrogen peroxide decomposes to these two products, and you can actually measure the rate of the reaction. So what we have here is the concentration of H2O2 as a function of time, similar to what I have there. These are actual, this is based on actual experimental data, right? And you can see here, this red line represents, so this is now, these dots here is actually experimental data. So you start at T0 with a concentration of, let's say, 2.5 H2O2, and as time proceeds, it's decomposing to form these products. The concentration is obviously going to go down, and it's going to form a curve like this. It doesn't always have to form a curve like that. The curve could be steeper. It depends on the so-called order of the reaction. We'll get to that in a moment. Now, notice these two lines here. This black line here represents the initial rate of the reaction. In other words, it's T0. Do you see that that line over there is touching the curve only at that point there? That would be the initial rate of the reaction, and we can simply take a change in the concentration over the change in time to get that rate. The actual value would be approximately 2.5 over divided by, let's say, 1,300 would be the rate at T0. But look what happens sometime later, after 1,500 seconds approximately, around here. If we now draw a tangent to this curve here, do you notice that the rate is going to be different because the gradient of this line is different? So the point is the rate changes as the reaction proceeds. Does everyone see that? And in order to actually determine the instantaneous rate at a certain point in time, one needs to employ, you need to use calculus to do that. Now, for any reaction, we can write a so-called rate law, a rate law. And a rate law is basically just taking a reaction. So here we have our generic reaction, A plus B forms B plus H. Little a and little b are the coefficients, little g and little h are stoichiometric coefficients of the balanced equation. And the rate law for that reaction is simply K, which is a so-called rate constant, times the concentration of A raised to the n, multiplied by the concentration of B raised to the n. Now, m and n, in those cases, in that case, or in all cases, has no relation whatsoever to the stoichiometric coefficient. Students often confuse this with equilibrium constant. This is something different. This m and this a are going to call reaction orders. So lots of new terms. Rate, this whole thing is called the rate law. This is rate constant. And these m and n is the order of the reaction. So we talk about the order of the reaction with respect to A, and the order of the reaction n with respect to B. Or we can talk about the overall reaction order, which is n plus n. Okay? So let's say, for example, if I have some arbitrary reaction, let's say A plus B forms C plus D. The rate law is simply Ka, as we see over there, Ka to the n, B to the n. That's the general rate law. Now let's suppose for argument's sake, n is 1 and n is 2. What is the order of the reaction with respect to A? It's first order. We say it's a first order reaction because the n value here is 1. We said it's a first order reaction with respect to reagent A. And it's a second order reaction with respect to B. That's what we say, with respect to A, with respect to B. So it's with respect to reagent A, it's first order. And with respect to B, it's second order. And then we talk about a so-called overall reaction order of the reaction, which is going to be what? 3. The overall reaction reaction order, so these are just terms, fancy terms. It's just going to be n plus n. It's going to be the overall reaction order. Rxn, this reaction order, is going to be 3, which means it's going to be a third order reaction. So we're talking here about kinetics, speeds, orders, rate constants, and rate laws. Okay. Now, let's look at these reactions one for one. Starting from here. If a reaction has a 0 order, right, so let's now suppose that we're looking at simple transformations. This is quite a complicated transformation because it involves 2 reagents. Let's look at a simpler case where we just have one reagent, A going to B, or X going to Y, it doesn't matter. A going to B. Okay, let's write that down. A simple reaction involving just one reagent. Right, one reactant, one product. Now, you have reactions like this, of course. You have, for example, particularly with salts and stuff like that, if you heat them up, they can undergo decomposition to gases and stuff like that. So we could have A goes to B plus C plus D. But let's just suppose, for argument's sake, A goes to B. You have many examples of this also in organic chemistry. We can have, like, say, for example, something undergoing some sort of conformation change or something. Okay? It's not important. I just want to keep it like this for the sake of simplicity. Now, the rate law for that reaction we can write down immediately. The rate law is going to be what? The rate law is going to be rate equals K A to the N, or N, or Q, you call it whatever you like. That's a matter of fact. It will always be like that. Now the question is, so this is the rate law. We call this thing here the rate law. Now let's suppose that N, by experiments, we find out that N, the order of the reaction is 0. 0. What will the rate law reduce to then? Just K, the rate constant. Remember, K is the rate constant. It's a constant with units. So if N is 0, then the rate law becomes rate equals K. Right, that's what we see over there. Now think about it. If you plot that, right, reaction, and it just depends on K, you're going to end up with a graph that looks like this. In other words, a straight line with a negative slope. If you plot the change in the concentration to the change in time, right, you get K in this case. So what does that mean? It means, let's suppose you have a reaction and you want to determine the rate constant, the kinetics of the reaction, you want to determine what the reaction order is, and you do an experiment like we saw earlier, you get a graph that looks like that, straight line. You can immediately conclude what? You can conclude that the reaction has a 0 order, like this. Now these reactions are quite rare. You do have them, but having a 0 reaction order is pretty rare. Yes?
Regularly speaking, but I just put it more like mass. So even if the one component that costs like A costs Y, then I don't know what it's chemistry, it's a reaction.
Because remember, if you take the change in, because what the rate represents, right? The rate represents, what is the rate? The rate is the change in the concentration of A over the change in time, right? That's the original definition we had. And we've just seen if the reaction order is 0, what does this reduce to? K equals delta A over delta T. And that is, per definition, the gradient, or it's a the gradient. So at all points in the reaction, you must get K. It can only be that if you have a straight line. Sorry, it should be negative. Because it's A is going to, of course, as time goes by, be used up. If we were looking at the reduction, so this is the rate of consumption of A, if we're looking at reduction of B, it would be a straight line going up. Okay? So that's the case for a zero order reaction. Now what we have here is basically, let's just look at this in a more formal way. The rate of the reaction is minus what I've just written there. Okay, I've used the delta there. But remember, in calculus, we can replace the delta with the d for a differential. Is everyone familiar with this? Okay. So the rate of the reaction is negative dA over dt, which equals K, right, per definition. And that is essentially nothing more than a so-called differential equation, right? So we can rearrange it. We can actually write. In fact, let's do that step for step together. I mean, I've got it there, but I want us to just do this really step for step. And this we call a so-called integrated rate law, because you'll see why in a minute. So as I've written here, we have dA over dt equals K. Now what I basically do is I take this dt up over there, right? I'm manipulating this equation. It's a differential equation, a very simple one. And I get that. Minus dA equals k dt. And what I can basically now do, if I integrate both sides, which is what I've done there, right? What I get is, what is the integral of negative dA? It's just negative A. Negative A equals K, because that's a constant, times T. This is integration. If you integrate 1, the integral of 1x, or just the integral of minus 1 dx is what? It's just minus x. So the integral of minus 1 dA is just minus a. Alright? Calculus. Calculus 101. Now, what I've basically done, the integration limits for time is from 0 to time t. So I'm integrating over time over here. And here I'm integrating over concentration. Concentration A0 and concentration AT. So the concentration at T0 and the concentration at some point in time T. And if I plug those values into this antiderivative here, I get what we have at the bottom there. AT minus A0 equals minus KT. And we can rearrange that, but that's good enough. That we call the integrated rate law. Now that's very powerful. Because if we have a reaction and we establish its reaction order as 0, we can use this integrated rate law that we've just derived, right? If we know the original concentration and we know the final concentration to determine a rate constant, or if we know the rate constant and we know the initial concentration, we can use this very elegant formula here to determine the concentration of A at some point in time t. So it's very useful, right? Does everyone see that? That's the case for a zero order reaction. Now let's move on and see what about the first order reaction. Now we'll do the whole thing all over again. Here we have a reaction where it so happens that the rate law, rate equals Ka to the n. In this case, n is not 0, it's 1. So the reaction is first order with respect to A. That's the lingo we use. So let's now erase all of this and do it all for a first order reaction. So we play the same game. We start off with a rate law. And in this case, n is 1. First order. So the rate law simply is rate equals K times A. Does everyone agree that times concentration? Now, we know, this is a fact of life, that the rate of the reaction is the change in the concentration of A minus the change in the concentration of A, because remember, it's a reagent, it's reacting away, divided by ET equals Ka. So the rate equals the change in the concentration of A over the change in time, which I can write as minus dA over dt. What I'm doing is I'm replacing the delta with d so I can use calculus to help me and make my life easier. I can't do that with deltas. That's the formal definition of rate. We know from the rate law that the rate equals Ka, so I can substitute, put these two equations together, like I just did for the zero order reaction, and I get, as you see there, minus dA over dt equals Ka. Now I'm confronted with the same situation, and what I can now do is I can basically manipulate that, right, to get an integrated rate law for a first order reaction. Let's do that together. What do? I have this as a starting point. So what I'm basically doing now is deriving an integrated rate law for this transformation. So I can rewrite that as minus dA equals Ka dt. I just take the ET up, did that earlier. And what I can now do is I can take this A down, this square bracket A. So I get minus dA over A equals K dt. And if you want to, we can take the minus across. Alright, we end up with that. Right, now we want to derive the integrated rate law, so what do we do next? We integrate both sides. Again, this is a basic simple differential equation. We integrate both sides, and we get, what is the antiderivative of this guy here? So this is now calculus. I have 1 over x dx. What is the antiderivative? Does anyone remember? Oh, no. It's ln. It's the natural log of x. You're all very nice. I guess you haven't done calculus, or who's not following the calculus? Well, instead of using x, just use a, right? So one has to know something about calculus. All you basically need to know is the antiderivatives of a couple of things. You'll see in a moment. The integral of dA over a is ln. So it's ln of a equals minus kt. And now I'll substitute the lower and upper limits into this, the limits of the integral into this antiderivative, and I get ln of a t minus ln of a0 equals minus kt, and I can rearrange that to get what I have on the right-hand side. That would be the integrated rate law for a first order reaction. Now, I think the only difficulty here, if you haven't done calculus, is going from here, from here to here. And to go from here to here, one needs to simply know from calculus that the integral of dx over x is the natural log of x. That's just a result from calculus, right? We didn't have the integral of dx over x, we got the integral of dA over a. So it's the natural log of a. That comes from calculus, so you use this result here. You don't have to now go and study calculus, you just need to know that one result. It's a result of integration, which is the inverse of differentiation. Okay, so that's the integrated rate law for a first order reaction. Now we can do the same thing for a second order reaction, but before we get there, for a zero order reaction, we just saw that if you plot the concentration to time, you get a straight line. Let's go back and have a look at that. And we discuss why that's the case. Now you can do the same thing for a first order reaction. If you plot the natural logarithm of the concentration, right, of that thing to time, or of the starting material, the natural log of the concentration of the starting material as a function of time, you also get a straight line. Then you know it's a first order reaction. And here's an example. So here we have that decomposition of H2O2 to water and oxygen. If you plot the natural log, in other words, if you do an experiment in a laboratory and you measure the concentration of the H2O2 as it's decomposing as a function of time, and you take the natural log of each of those concentrations and plot them, and you get a straight line with a negative gradient, it is a first order decomposition reaction, basically. The reaction is first order in the concentration of H2O2, and that's what it looks like. Now, very important thing is this. Do you all see that the slope of this line here is negative k, the rate constant? Why is that? Because of that. You see that? Okay. So if we have a first order reaction, we'll summarize this all nicely at the end. Okay. Just hang in there. The worst is nearly over. You look very confused and frightened, don't we? So let's now go to a second order reaction. Okay, we're getting a half-life, and I don't want to discuss it this time. A second order reaction. If we do exactly the same thing, but now instead of having a reaction Ka to the 1, we have Ka squared. In other words, the reaction is second order in A, right, or in the concentration of A. You can play the same game using calculus, doing the same thing we've just done for a zero and a first order reaction. And you get this is the integrated rate law. Alright? Why is this important? Again, if you have the integrated rate law, you know the order of the reaction, you can mathematically determine the concentration of something at a certain time t, if you know the rate constant, or vice versa. If you know the concentration at some time t and at the starting concentration, you can work back and determine the rate constant, k. That's very useful, because the rate constant is a signature of a reaction, right? Where the rate constant for a specific reaction under certain conditions will always be the same, right? Of course, you have to look at the temperature, pressures, concentrations, but it's a certain signature of a reaction, and it's sort of, that's why it's called a rate constant. It's a constant, right? Okay, so let's just quickly go through this again. Let's go through this, why not, from first principles. So we start off again here. By the way, the derivation of these three rate laws, I think, I want you guys to be able to do. This is important. So now we happen to have a second order reaction, or at least let's say second order in A. So the rate law is rate equals Ka, the concentration of A squared. We also know that the rate of this reaction, the transformation of A to B, is negative the change in the concentration of A over the change in the concentration of time. That's a matter of fact, isn't it? We can rewrite that as minus dA over dt. And now we can use calculus to derive the integrated rate. So how do we proceed? Well, we say set these two equal to each other, right? So Ka squared equals minus d K over T. Alright, what do we do now? Well, we take this A down. So we're going to have, let's see, we're going to have, yes, we're going to have A squared over BA equals 1 over KET. Yes, yes. Is that correct? Oh, we take this down, we take that down. That's the thing. Yeah, this is correct.
Is it because you said those C equals each other? You get
Yes, that's what I have. K squared equals negative BA over ET, which is just an alternative expression of the rate law. This is correct. This is correct. Okay, so what we can basically now do is, well, we can flip everything around, can't we? Yes, we can do that. So we're going to get minus dA over A squared equals KET. Yes, yes. I've just inverted everything. And if you now integrate both sides, yes, if you now integrate both sides, you figure out what's the antiderivative of that integral, which is of the form 1 over x squared dx. You basically end up there. The antiderivative is going to be like 1 over a equals kt. Let's do it. So the integral of 1 over x squared dx is x. 1 over x, sorry. And so you can use the antiderivative of this integral expression and you end up here. Yes? Oh, it's here. It's here. Sorry, it should be outside the integral.
Why is it on the board as a key integral?
Oh, well, if I integrate KET, I'm going to then get KT outside as the antiderivative. The integral of constant times dx or dy or dt is just kt, that's the antiderivative. And the integral of dA over a squared is minus 1 over a. Sorry, it's just 1 over a, but there's a minus sign in front of the integral. Alright? And that a now needs to be, well, we're integrating over concentrations from a0 or a at t0 to a at time t, and we end up with that expression at the bottom there. And then you can basically play the same game. Now again, this is what the integrated rate law therefore of a second order reaction. So if I go into a laboratory and I know it's a second order reaction, I can use this integrated rate law to determine K for that reaction, the rate constant. Well, if I know the rate constant, I can determine the concentration of A at some point in time t using the integrated rate law. You know it's a second order reaction by looking at the data. In other words, if you go into a laboratory and you have an experiment going on, and you, as a function of time, determine the concentration of that reaction, and you plot it in this way, you get a straight line, you know that's a second order reaction. So, let's summarize. If we're not talking about simple transformations A to B, right? We're keeping it that. I'm not going at this point to make it more complicated. If it's zero order, what does the graph look like? If it's zero order, the concentration to time is of A going to B is a line going down, a straight line. right? And the gradient of that line is the rate constant. Okay, that's a zero order reaction. The first order reaction, what did we see? If we plot the concentration, the natural log of the concentration as a function of time, and we get a negative slope, the conclusion is it is a first order reaction, and its slope is, the rate constant is minus the slope. If the reaction is second order, and we plot the inverse of the concentration as a function of time, and we get a nice straight line from the data, what's the conclusion? The conclusion is it is a second order reaction with respect to A, and the rate constant is the slope of the curve. So if you're in a lab and you have a reaction, and you get all this data, you simply perform those three plots, and from those three plots you can determine what the order of the reaction is. If you plot the concentration as a function of time and you get some weird looking graph, it's not zero order. If you plot the concentration, the natural log of the concentration as a function of time and you get a nice straight line, you know that it's a first order reaction. If you get a funny looking graph there, it's probably not a first order reaction. If you plot the inverse or the reciprocal of the concentration as a function of time, you get a straight line like this, the conclusion is it's a first order reaction. And from these graphs you can determine the rate constant, K. And you can employ the integrated rate law for each of these reactions to actually do all sorts of things, like determine concentration at certain points in time, etc., etc. Now, unfortunately, we don't just have zero first and second order reactions, we also have third order reactions, fourth order reactions, fifth order reactions. But you can basically generalize the the reaction rate law, or the rate law of an nth order reaction. I don't expect you to know this, but this is just a question of calculus. You can write a general formula from the rate law, Ka to the power of n, and it looks something like this. And that, by the way, is sort of a general solution. If you know n, you can plug it into that equation over there, and you will get the integrated rate law for an nth order reaction. And that's actually quite useful. We've now done it for zero first and second order reactions, but there you have it. Now, let's just go back to this graph over here. Let's just go back to the beginning. This is concentration over time, that's zero order. This is the natural log of the starting material, the concentration over time, straight line, first order. And second order looks like this. So, I just want to see something here. All right, well, here we've got three reactions. And this is not very convincing, is it? Okay, well, sorry. I was just not out of my order there for a moment. I'm back in order. Here we have an example of a reaction in a laboratory. We have a transformation A going to B, and we have this data. This is what I was talking about earlier. So you have a scientist or a student that's changing the concentration as a function of time. He plots these three curves. He plots the first curve, which is just the concentration as a function of time, and he gets the curve. Is the reaction zero order? No. Because if it were a zero order reaction, what would we get if we plot the concentrations as time? Straight line with negative slope. That's not a straight line. So it's not zero order. Then he says, okay, it's not zero order, what's the next thing I do? Let's take the natural logarithm of each of these data points and plot those as a function of time. And he gets a curve that looks like this. Is that a straight line? No, it's still a curve. Is it a first order reaction? No. Then he takes the reciprocal of each data point, so 1 over the concentration of A at each of these time intervals, and he gets a straight line. What is the conclusion? It's a second order reaction like it is here. So, but that's what you were doing in lab. If you want to determine the order of a reaction, you just simply get the concentration as a function of time. You plot it, you see if there's a straight line. If there isn't, you plot the natural log as a function of time. If that doesn't work out, you then plot the reciprocal as a function of time, and so on until you get a straight line, the radiant of which is k, the rate constant. Yes?
No stupid question.
There's no stupid question.
Why do you need to know the order of it?
The order of a reaction is very important in making certain predictions concerning mechanism and understanding how a reaction actually works. And if you, for example, want to accelerate a reaction, for example, if you're a scientist that's wanting to make some very useful product, knowing the kinetics helps you to design better catalysts, because so it's important in terms of mechanistic considerations.
So I feel like it's calculus before parameterization. So I'm like trying to like mimic those words like is the second is like x to the higher order of O and I'm calling that like x to the, for example, second, and then if you give like 1x to the first, and then it's just 1x.
Yes, that's differentiation. Consideration is the inverse. For this class, we need to know 3 antiderivatives. The integral of 1, which is just, A, because we're working with A on A. It's the integral of 1 over A, which is the natural logarithm of A. And the integral of 1 over, the integral of A squared over A. The integral of A squared over dA, which is minus 1 over A. So those are the only 3 you need to know to be able to derive these 3 radials, 0, first and second order, that I expect from you in this case. I just show you for the sake of your own amusements that you can generalize this to n, and then you get an integrated radial for any nth order reaction like that. And you can derive this very simply using calculus as well. You don't have to do it, because I know that this is difficult. All right. Let's go on. So that's now a bit about 0, first and second order reactions, the rate law, the rate constant, the order of the reaction, how we can determine the rate constant, etc., etc., etc. By the way, the units of the rate constant K is going to depend on what? It's going to depend on the order of the reaction. You see that? Because if I know the rate of something, the rate is a constant, it's going to be the rate constant, the units of the rate constant is going to depend on the order of the reaction. Now, it could be moles per second, etc. Moles per decimeters cubed per second, etc., or per second squared, so it depends. All right. Here we have a nice example. Here we have a very nice example, again, in a laboratory situation. This happens to be the decomposition of acetaldehyde to carbon dioxide and water, if I'm not mistaken. Anyway, it's a decomposition reaction of an aldehyde. And what the scientists have done is they've, at different concentrations of A, measure the initial rates of the reaction. You see that those are the units, moles per decimeter cubed per second, should be per second. Now, let's see what this means. This is the initial initial rate of the reaction that they've measured. Okay? If you increase the concentration, obviously the rate's going to increase, isn't it? If you increase the temperature, will the rate increase of the reaction? Yes. If you increase the surface area, let's say if it's a solid reacting with something, will that increase the rate? Yes. So there's factors that increase reaction rates. Temperature, the higher the temperature, the higher the reaction rate. Pressure, well, it depends on the situation. And concentration certainly as well. The higher the concentration, the faster the reaction is going to proceed. So what we have here again, this is just a simple decomposition reaction, similar to what we had with H2O2. You know, remember that reaction we had one in the beginning, H2O2 going to water plus oxygen. This is something like that. And what these guys have done is to change the concentration and measure the initial rates. Now, this is a nice question. So let's do this together. From this data, determine the order of the reaction with respect to A. So, all we know at this stage is we have all this nice data, and we're going to say rate equals K A to the N. That's the rate of the reaction. And we want to find N, don't we? Now here's a question. How do we solve that problem? How do we determine the rate, the order of the reaction with respect to A from the data that we give? Does anyone have any ideas? We don't have time. That's a fact. We don't have time. If we had time, what could we do? We could plot it. Like I just said, you could plot the concentration over time, you could plot the natural log as a function of time of the concentration, and you can plot the reciprocal concentrations over time and see what you get. And from that, you can determine if it's 0 versus second order. But what else could we do? Something like that, yes. What about this? Just look at this equation, right? From this equation, we know